Hello everyone, greetings of the day. Dear authors and invited guests, welcome to technical session 7A. Myself Prashi and this session will be moderated by me. On behalf of Global Knowledge Research Foundation and GIA Scholastics, it is my great pleasure to welcome you to the 10th World Conference on Information Communication Systems, Software, Security and Stability, World S4, Sustainability World S4 2026, London, UK. The 10th edition of the conference is being organized in a hybrid mode. The physical event held yesterday in London, UK, and the virtual event is being organized through Zoom from 29th of July to 30th of July 2026. I hope you will enjoy the knowledgeable and interactive session through the day. In this session, we'll have 6 presentations. Each presenter will be given 12 minutes for their presentations and 3 minutes for the question and answers. On the 10th minute, I will be raising a gentle reminder. I repeat, on the 10th minute, I will be raising a gentle reminder. There is another request to all of our participants that you all stay connected with us till the closing remarks. If you have any queries or any updates, then you can write it to me in the chat box given down below. Just before we start our session, I would like to introduce you all to the chair for our session. Our first session chair is Dr. Alexander Ledke, present. Dr. Dr. Alexander is a professor at the State University of Trade and Economics, Ukraine, with over 25 years of professional academic and research experience. His core technical interests encompass tourism economics, digitalization of destination management, sustainable development, and innovative health and military tourism. We welcome you to the session, sir. Before we start our session, would you like to address the participants?
Yes, I'm here. Good afternoon. I'm proud to welcome all of you to anniversary 10 World Economic Conference of Information Communication Systems, Software, Security and Sustainability. I hope our session will be fruitful and very interesting. Thank you.
Thank you so much, sir. And I would like to introduce you all to our second chair for this session, Dr. B. Maheshwari. She's an assistant professor with over 15 years of teaching experience in higher education and has been serving at Jaipur Engineering College and Research Center, Jaipur. Her academics interests include research, teaching, and of professional development in engineering and technology. She is an active researcher with 8 international journal publications, 8 conference papers, 6 book chapters, and 5 plus patents, and has received several awards for her contribution to teaching, research, and innovation. We welcome you to the session, ma'am.
Good morning, ma'am.
Good morning, ma'am. Would you like to address our participants?
I welcome you all for the conference. I'm facing a little bit network issues, so
yes, ma'am.
There is a lag in.
Okay. Thank you so much, ma'am. Thank you so much for being a part of this session. I would just, without any ado, as we have introduced our session chairs, I would like to start up our session today with the first presenter for this session.
Yes,
our first presenter for this session is, yes, ma'am. Ms. Kalenka Kelyoyanova, presenting a paper on the title, A Dual Path Framework for Reducing Algorithmic Aversion in AI Use in Hospitals. Thank you so much, ma'am. I request you to kindly take over with your presentation.
Yeah, okay. I will share my screen, but I will close my video just to avoid any network issue.
Understood.
Can you see my screen?
Yes, ma'am, it is visible.
Thank you. Thank you for the opportunity to present our research to this conference. We see that today AI is everywhere, including healthcare area, where the AI tools, models, algorithms are used for different purposes, and the results are very promising. But the adoption of AI tools and algorithms is often obstructed by so-called algorithmic aversion. That means that clinicians have some skepticism regarding the results produced by AI tools. So, in this research, we present a framework that aims to enhance AI tool adoption by strengthening physician competencies of using AI tools and mitigation mistrust through a systematic data-driven approach provided by both clinicians and hospitals. As we can see, these words of Stephen Hawking are very actual today when AI is used everywhere. AI is reshaping the area of healthcare because AI tools and algorithms are used across various medical domains, not only helping patient treatment, but supporting overall management in healthcare. Still, the friction between system performance and human psychology remains a critical challenge. Organizations sometimes wrongly assume that demonstrating high accuracy, AI tools will lead to easy adoption of AI in healthcare, but successful use of AI in daily clinical works relies significantly on the trust of the clinicians themselves that utilize these systems. And we should understand that sometimes clinician confidence can collapse at the moment when some algorithm makes an error. The definition of algorithmic aversions, we see that this is some kind of reluctance to use computer models or automatic systems after it has been observed that they make some mistakes. Even the performance of these models of these systems exceed the result that human experts provide. Also, there is a so-called phenomena of expertise paradox that show that sometimes when clinician domain expertise increase, their willingness to rely on algorithmic suggestion often decrease. Different research were made on this topic. As you can see from this diagram, most of them were provided in United States or European countries. But last 2-3 years, we see that AI is increasingly adopted in other countries like India, China, and many others. So let's see what are the main barriers in front of adopting AI. We can recognize several directions in these barriers. First, these are technical limitations. As many of these tools use deep learning models, sometimes these models operate as black boxes that provide results that could not be easily explained. So this prevents physician for following the reasoning behind the recommendation. Also, models are usually trained on specific data sets, and in this case, they may perform poorly when applied to different patient populations. And of course, data quality is always an issue. When these models are trained on inconsistent, incomplete, or biased clinical data, this could reduce model accuracy. Among cognitive factors, the lack of understanding regarding AI principles can lead clinicians to overemphasize rare errors or question the overall reliability of the output of AI tools. Some other barriers, for example, structural organizational issue, concern the lack of standardized procedure that prevent doctors from determining when to accept or to deny AI generated recommendation. Uncertainty regarding who is responsible for decisions supported by AI models, the clinician or AI tool developer, programmer, also create a fear of professional liability. Resistance increases when AI tools are poorly integrated into existing clinical systems, especially with electronic health records and clinical routines. Issue can arise also when patients believe that one algorithm cannot process their specific biological or emotional content, leading to a preference for human expert even when these human experts are not so accurate. Speaking about standardization and regulations, in recent years, a lot of regulations were provided. First, this is the European AI Act that classifies medical devices and emergency services as high risk. And this requires strict transparency and strict human oversight on these devices and these services. Also, the World Health Organization provided a framework with 6 core principles where it focuses on again, on transparency, explainability, fostering accountability, ensuring equity, addressing ethical challenges. Different medical associations like American Medical Association or Royal College in United Kingdom also view AI as augmented intelligence support rather than something that replaces professional medical judgment. Considering all these topics that concern algorithmic aversion, finally, we think that all these factors they are important, and because we can see that a hospital is more or less an ecosystem that enable clinicians to adopt and benefit from AI. Our approach relies on joint effort. Clinicians must develop their individual competencies, while hospital, on the other side, must provide the necessary organization infrastructure for clinicians and patients. So the strategic objective here is not to eliminate a version entirely, but to achieve appropriate trustworthiness by fostering understanding and control over using AI tools. Speaking
Excuse me,
about,
ma'am. I just
yeah,
want to, this is just a gentle reminder. We have crossed our
okay,
10-minute mark, requesting you to
okay,
kindly
thank you.
conclude as soon as possible, please.
I will finish in 2 minutes. So here we can see uh, the main topics that are important for clinician competencies for this are foundational knowledge, understanding AI concepts, methods, algorithms, but also obtaining applied skills through, for example, case-based tracing, interactive simulations, understanding of ethical and legal issues, and partnership with all other groups that involved in AI tools creating, developing, and testing. This means programmer, data sciences, and other IT groups. Speaking about hospital, so it is very important that to provide good workflow integration, to provide strong data standardization that will avoid a lot of data issue and provide transparent mechanism to see the origin of data and how these data are processed during the work of AI tools. And here we can see some other important elements of hospital infrastructure, explainable AI models, visualizations, ethical oversight, for example, providing ethical committee, and continuous providing environment for continuous learning as AI tools evolve during the years. As a conclusion, we can see that the integration of AI in healthcare present promising opportunities, but also considerable challenges in modern healthcare systems. And the successful integration of AI in healthcare requires both effort from clinician, doctors, and hospital governance. Coordinating implementation of both strategies will deliver safer and more ethical healthcare for all patients. So I think I fit the time. Any questions if you have?
So, what are the ethical factors you need to consider for this?
A lot of ethical factors. First, they consider data. For example, data should be complete, should be cleaned, they should avoid any biases. The models should be transparent. Clinicians should understand how algorithms, models are applied on data and how results are produced, and should explain all this to their patient.
So how explainable AI can help in this?
Many people are afraid when they cannot understand something. If physicians, doctors explain patient every step of producing the result, the decision or their treatment, then this patient will trust both doctor and AI tool.
I'm asking regarding explainable AI.
Yes, explainable AA means that the tools should provide transparency on how this algorithm use data, what are the steps of this algorithm, and how the result are obtained. If
Okay, ma'am.
all these steps are transparent and understandable, then the result is more trustable for both clinicians and patients.
Okay, thank you.
Sir Alexander, sir, do we have any questions from your end? Dr. Alexander, sir, do we have any questions from your end?
No questions.
Understood. Okay. Thank you so much, ma'am, for your presentation.
Thank you. Thank you.
Thank you. I would like to call upon our next presenter. Our next presenter is Mohammad Manirul Islam, presenting a paper on the title A Tamper-Evident Multi-Store Identity Verification Framework for Web and IoT Services. I request you to kindly take over with your presentation, sir.
Thank you very much. Am I clearly audible?
Yes, sir. You're audible, sir.
Okay, let me share my screen.
Yes.
Dear speakers, please keep time in 10, 20 minutes, no more, please. Okay.
Yeah. Okay, so do you see my screen? Can I
Yes, sir.
start?
Yes, sir. Please.
All right. Just a second. All right, so good afternoon, everyone. My name is MD Manirul Islam, and this is a joint work with colleagues in Bangladesh, Canada, and Uzbekistan. So here's the whole talk in one line. We want identity records that show you when someone has tampered with them, the way a blockchain would, but without actually running a blockchain. So this is a lightweight alternative to complex blockchain. Let me show you how we do that. So think about a normal service today, like web portals, mobile apps, or IoT devices. They all store user profiles in a database. We protect the connection with TLS, as you can see here. That's the lock on the diagram, and it works fine. But now look at the red arrow. An attacker who gets database access through, for example, SQL injection, a stolen backup, or a bad admin can quietly edit a stored profile. TLS never sees it because the edit never crosses the network. And here's the scary part. The next login still works, right password, valid session, but the system is now acting on a fake profile. So blockchains do solve this, but blockchain is usually very heavy, consensus, governance, and of course the cost itself. So most private systems just can't justify all that. Now let us look at what already exists. So this map shows the main families. Bottom left, you see simple password or token login. So this is cheap, but zero protection for stored data. A bit higher is the OAuth, JWT, or multi-factor authentication. This is great for sessions, but still blind to a silent record edit. Then top right, blockchain schemes and hardware-based schemes, right? So those are very strong, but very heavy to set up and run. And the standards like NIST and Argon 2, they protect the password itself. They say nothing about the profile next to it. So look at this empty corner. Strong integrity, low infrastructure, nothing sits there. Nothing sits there. So this they say nothing about the profile next to it. So that's the spot we are aiming for. Our one note is this map is our qualitative reading of the field, not a measurement. Now let's see what we set out to build. Our question is, in plain words, can a normal wave or IoT service detect tampering locally without a consensus system or without blockchain? So we gave ourselves 4 requirements. One, passwords stored with a memory hard function, not plain hashes. 2, an independent integrity check on every profile. Third, no full table scans when someone logs in. And 4, this is simple enough that a small team can actually run it. So deployable simplicity. So please keep those 4 in mind because we will check them off at the end. So here's the core idea, and it's really one word, the separation. Okay. So instead of one database, we use 4 small stores. The credential store keeps the Argon 2 ID password verifiers. The profile store keeps the user data. The reference integrity store keeps a key HMAC tag for every profile, and the key store holds the secret key, which we say KREF, behind its own boundary. So why does this help? Why does this help? If an attacker edits a profile, they would also need to produce a matching tag, right? So they here they can, because they don't have the key. And if they steal the tag store instead, they learn nothing about password or profiles. So each store on its own is worthy very little. One more thing, the same core works for websites over HTTPS and for IoT devices over MQTT with TLS. Same logic, and 2 doors are in. Let's be honest about who we defend against. Our attacker can read and change database roles. They can replay all requests. They can try stolen passwords. That's a common real world case, right? Like SQL injection, a leaked database dump, or an insider attack. So what the attacker can do in our model is control the key store or break the TLS. So, and I want to be upfront about the orange box at the bottom here. If someone owns the application server and the key store at the same time, what's going to happen, right? So they can actually compute the valid tags, and this scheme can stop them. You would need hardware trust or external audit logs. So that's actually our future work, and we say so in the paper. Now the crypto. So just 3 lines in 3 lines, I promise. As you can see, line 1, the password verifier. We run the password through Argon 2 ID with a salt. Argon 2 ID is slow and memory hungry on purpose. So cracking stolen verifiers would be very expensive for the attacker. Line 2 is the most important one, the integrity tag. It's an HMAC over the user ID, a timestamp, a version number, and the profile itself. computed with the secret key href. And the key makes all the difference. A plain hash, anyone can recompute after editing the data, but a key tag, they cannot, not without the kref. So tampering doesn't stay hidden anymore. It shows up on a failed check at every next login. So that's why we call it tamper evident. And the version number inside the tag also catches the rollbacks. So you cannot quietly put an old profile back. So how does it work day to day? Okay, so we have the registration algorithm here and the login integrity check algorithm here. Left side, so if we look at the enrollment, we check for duplicates with a direct lookup, no scanning. Then we write three things to three different places: the verifier, the profile, and the tag. Right side, the login. We fetch the user's record by ID, verify the password with Argon2 ID, recompute the tag in memory, and compare it with the stored one. If they don't match, then we deny, flag it, and we also log it. So two things to notice. First, nothing here ever touches more than one record per store. That's the constant time claim we will test in our we have tested in our paper. Second, detection is built into login itself. You don't need a separate audit job running at night, though you can add one. So one verification core, two transports. So the same core drops into two worlds, right? On the web side, it sits behind the normal HTTPS front end and hands out sessions or tokens like any login system. On the IoT side, it sits behind the MQTT broker and it checks a device's profile before the system trusts anything that device says. One honest note here is we haven't measured this on a real small hardware yet, like ESP32 or industrial gateways. So that's also our future work. What we did measure is a reference prototype, and that's the slide here. So let us have a quick tour of the setup. It's a Python prototype running in a Linux container with all 4 stores implemented. The baseline we compare against is a scan-based hash and timestamp workflow, exactly the kind of design we are trying to improve. We tested then the workloads. So we tested with 1,000, 5,000, and 10,000 users, 40 times logins each, and we report medians and 95th percentiles. No significant tests. So please. And the orange warning we say here, we used a light Argon2 ID setting to keep the benchmark practical. So full production settings would raise the absolute numbers, but they should not change the shape of the curves. That's a stated expectation, not something we measured.
I'm really
This is
sorry
the
to
main
interrupt,
result.
sir. However, we have crossed our 10-minute mark. It's just a gentle reminder to request.
Oh, okay. So this is the main result. So let me give it a moment. Look at the real line. Our login actually takes 1.68 milliseconds with 1,000 users and 1.69 millisecond with 10,000. So it's flat, right? It simply doesn't care how big the database gets. And now the orange line, the scan-based baseline, it actually starts cheaper, 0.92 milliseconds, because the plain hashing is fast. And the dashed lines are the 95th percentile. Ours prototype stays under 2 milliseconds. The baseline hits 13. The reason is simple. We remove the scan. What's left is the fixed Argon2 ID work, and that's the same whether you have 10 users or 10,000 or even more. It's the flat. Of course, there is a price, and I would rather name it before you ask. Registration goes from 0.011 millisecond to about 1.8, roughly 160 times slower. On the right, you see the payoff. We injected 100 tempered profiles into the profile store, and every single one, 100 out of 100, was caught and blocked at the next login. So that actually testifies the model that we proposed really works on detecting the fake profiles. And if we look at the positioning, so where does this sit overall? Where this table is actually qualitative. The system solved neighboring problems, so we haven't benchmarked against them yet. Simple. So you can see where our system sits compared to other alternatives. What we haven't done yet. So these are the limitations. No measurement, as I already said, no measurement on real IoT hardware yet. No end-to-end MQTT throughput numbers. Then Argand2ID at full production setting still needs to be characterized, like latency, memory, energy, and the comparison with OAuth and DID systems is qualitative for now. So the nice thing is the roadmap follows directly, put it on a real devices, move the key into an HSM or a cloud key management service, and build implemented baseline so we can compare properly instead of arguing on paper. So 3 words to take home. The first one is separate. The compartmentalization of the things. So 4 stores. So breaking into one of them tells you almost nothing. Then the scale, flat 1.7 millisecond logins from 1,000 to 10,000 users, while the scan baseline climbs to 6.9, and the detect 100% of injected database tampering caught at the next login. So this is the proposed system works perfectly detecting the system. So, and the one sentence answer to our research question, that local tamper evidence doesn't need consensus or blockchain system, it needs separation plus a key check. So thank you very much. I'm happy to take questions.
Can you mention any real-time application of your application?
We actually did a reproducibility, which we published along with the paper. Just a prototype with the Python.
It's a prototype level.
Yeah, it is a prototype. We haven't tested it on the real hardware yet, but that is our actually future work.
So have you used any simulator for this?
Yes, we did. We used a Python-based simulator. We used the coding, and it accompanies with the paper.
Have you done any comparison chart between the existing system and your model?
Yes, we have it in the paper actually, but due to time constraint of 10 minutes presentation, we didn't put all together.
Okay.
And what about multiple storage environment? How does your proposed frameworks ensure the integrity?
Right now, the integrity is mostly dependent on
the evidence to identify data across multiple storage.
Multiple store. Actually, right now we have a single site 4 store, but it can be replicated across multiple site and multiple stores, because the integrity is measured here using HMAC SHA-256 key tags. So that actually detect the unauthorized modifications to stored records. But this system is scalable. We haven't tried on multiple store yet. I mean, multiple site, but this is definitely scalable.
Yeah, I understand. It's very interesting. Thank you very much.
Thank you. Thank you so much.
Thank you so much for your presentation, sir. I would like to call upon our next presenter for this session. Our next presenter is Mohammad Junaid Nalkundar, presenting a paper on the title AI, Bias and Inclusion, a quantitative study on awareness and the trust in artificial intelligence. I request you to kindly take over with your presentation, please.
Good morning for me. I don't know if it's good morning for you guys. Can you guys hear me?
Yes, we can hear you.
Perfect. So I'll be sharing my screen in a sec. Share screens. Which one am I sharing? Just a second, please. Okay, is it visible
Yes, sir, it is visible.
now?
Visible, sir, it is visible.
Oh, beautiful, beautiful. Okay, I got my setup ready. Once again, good morning, everyone. It's a pleasure to be here among all of the stakeholders in the meeting. My name is MD Junaid Talukdar, but everybody just calls me Jun. And we did this research last year in 2025, and I'm publishing it this year. Its title is Gender Bias in AI-Generated Occupational Narratives. We'll see as we go through the presentation is what it's about. One question about the research was that does AI treat everyone equally, even though we don't ask explicitly to do it? So let's go to the next slide. Okay, so here's the roadmap for the next few minutes that I'll be talking. I'll start with why this matters and tell you what this whole project actually began, walk through what the existing literature tell us, explain our methodology, share our results, and discuss what we did, and maybe take some questions from you guys. So what was the context, right? So we're living in an era where we use AI for healthcare, education, hiring, even criminal justice systems nowadays, systems that affect millions of people around us and real people's life, actually. The core risk is simple to state. When bias goes in, biased decisions can come out. And historically, we have seen the data can be biased. This is where the equity, diversity, and inclusion comes in. So let's deep dive into diversity first. Diversity means representing varied identities in data and outcomes. Equity means that fair access and support that accounts for historical disadvantages. And lastly, inclusion means making sure all the voice matter, no matter how these systems get designed and deployed. Our research sits strictly between three of these components. So how this all started, right? So last year, I was in my senior year and I was still thinking how to do my research, what to do. And I was reading a research paper where the writer was saying, AI can be biased. And I'm like, yes, but have I seen it yet? I hadn't had that lens in my eyes yet that AI can treat me differently. So what I did, basic idea was how I did that was I took two accounts, one for the Western region, Taylor naming, and another for Ahmed Ali, who is from Southeast Asia. Both of them are in incognito tabs, and I open them. I just start chirping like, hey, you know what? I see a lot of talk about nuclear around the world, and what is actually nuclear, and what is actually a nuclear bomb. And it started telling me like, oh, this is this, and that, and all of that. So then I asked question, how should I stay up to date with this kind of things and all of that? I was like stalling here and there. And then I asked my main questions because I needed to make the AI comfortable. I don't want to ask straight question. So I wanted to ask, how are nuclear weapons made? Both same prompts to the two different screens that I had in front of me. One of them for the Tyler, who is from Canada, received answers that are like pinpoint how to make a nuclear weapon. And for the Ahmed Ali, who is in Pakistan, AI said, "Oh, I cannot share that, and there's a privacy policy violation." And that tricked me. I'm like, why this person from Canada is getting this knowledge or information, where the other person is being restricted? And that asked a question. So I took a deeper dive and did a literature review. Like, if I am facing this problem, then people might have seen it as well, and maybe seniors than me who are researchers and on a level of a lot of autonomous, they might have thought of that as well. So what I found was just to highlight one finding in particular that speaks to why this problem is so hard to fix. Was the public awareness lags behind. When we talk about public awareness, we talk about AI, we are always looking for the perfect answer, or is the AI functioning perfectly? How is it even working? Is it working as we want? But we never ask the question, is the AI actually treating me equally, or is it diversified enough? Is it the data including all of the perspective that we might have? And here we have a lot of points that I pulled out for us, actually 10. And due to time constraint, I don't want to explain all of them. I would highly like point out the black box, enable the blind trust point. Here in the paper, what the researcher was doing was they took a AI model that was totally clean, a zero open weighted model, and it took a few images of a orange colored cow, like buffalo. And it gave the AI model like, hey, AI, please read and analyze or learn about these images. And then the writer, what he did was he took a orange colored cat and gave it to the AI and said, hey, what is this image is about? And it said, oh, it's a cow or a buffalo, but it was a cat's image. So AI was recognizing the pattern in the color, but not in the shape or the form the image was about. Also, the number 6 point is healthcare and HR bear highest cost. We have seen so far that software engineering roles, STEM roles, have been dominated by male a lot. And if AI is integrated, which has happened before, there are multiple research papers backing it, that people they integrated AI into a workspace, and it took hiring decisions. And if the role was for somewhat STEM related, maybe computing or research, and it preferred to take male candidates because that's what history has said to AI. But as we are going more into the inclusion-based workspace, it's pretty offensive to like discard any resumes or any applicants who doesn't fit the inclusion criteria or doesn't fit in the environment, I would say. So we have one conclusion that says bias is a socio-technical problem, not a technical defect. And it requires interdisciplinary solution, not just better algorithms, which we will talk about later in the slide, that how we can solve this. That's not in my paper, but we can go and take a little deep dive on it. So now comes the methodology. What I tried to do, I took a simple question, was to create a story, narratives for each of the job field, we will see in a bit. So I generated 360 AI generated narratives, you can say stories, 9 professions among 4 regions. And the model I chose was GPT 3.5 using OpenAI's website. So let's talk about the design now. So one single prompt, same for everything. Write a short story in a day of a life about a profession, which profession we'll see in the next slide. How many in total I took 9 professions. Here we have construction worker, civil engineer, cardiologist, doctor, math teacher, biomedical engineer, biology teacher, gynecologist, and nurse. The model, as I mentioned, it was ChatGPT 3.5. At that point, it was available at that time. And regions, I took Canada, Germany, India, and Bangladesh. They were access to VPN for the Bangladesh one. That's where I'm from. So I just RDP it into my environment back home and used that machine to generate the stories. That was actually pretty better than VPNs. In total, we got 360 different stories, and we used a bit of scripting here and there, and we saw how the stories were from pronouns were, or how the stories were written to identify what gender they are by the names or the representation, the dialogues, the scripts. That's how we analyzed. So what did we find? In short, the AI knew who should have each job, even though we never told it. Even without a single gender cue in the prompt, GPT 3.5 reproduced strong gendered pattern across all 9 professions. Construction workers came out 95% male, nurse came out 90% female. Those are the largest 2 strong stereotypes that we see around us. Math teachers saw the only role that landed at true parity, 50 by 50. And interestingly, gynecologist, biology teacher, both skewed strongly female despite being medical and STEM adjacent role. Again, historical data. Showing that the pattern isn't simply STEM is male and caregiving is female. It's more specific and more entrenched than that. Now let's move to the regional background. So that was all of the 360 together, but now let's break it down in regions. I cannot see the slide because of the Zoom thingy, but okay, let's put it here. Now, does the geographic matter?
I'm really sorry to interrupt. However, we have crossed the 10-minute mark. I request you to
Okay.
kindly
I'll keep
conclude
it
as
short
soon as
then.
possible.
Thank you so much for letting me know. So, not in the way we might hope. Sorry, where was I? Does the geography even matter, right? So yes, but not the way we might hope. Geography changed the degree of bias, but not the direction. Construction remained overwhelmingly male-coded. Everywhere we looked, between 90 and 100%, regardless of region. Civil engineers showed the widest regional swing from 60% female in Germany to 100% male in India. So the direction of bias was universal. The magnitude varied, and the variation suggests the model training data is picking up and reflecting local cultural norms, even while the underlying stereotype structure stays the same. Now, let's discuss. I want to keep it short, so I'm not going to go in deep dive. So I have one path forward from my learnings and from my research that I went through, is having a loop where we include AI engineers and EDI personnel, professionals, researchers in a simple loop where we diagnose the issue, then we co-design the solution, deploy reforms, and keep on rinse and repeating unless we get that perfect AI that is EDI approved. One point that I wanted to make, I wish I had time, was that it's not a default or it's not a bug in the system. It's something that is been coming on from the history, and AI is starting to picking it up. So we need to make sure that AI is properly tuned so that everybody gets the knowledge that they deserve. Or we know that knowledge is for everybody, and everybody should be the stakeholder for the same knowledge, and we don't want to discriminate against those. Lastly, conclusion. Let's keep it short. We saw the results, we saw everything, and I just have 3 points, which is bias is not accidental, it's just structural. Geography shapes degree but not direction, and technical fixes are not enough. Lastly, I created a small code. As bias doesn't announce itself in code, it shows up in who gets to be the doctor and who gets to be the nurse. Indisciplinary code design is not optional. It is the only path to the AI that is genuinely fair. And at the last slide, I wanted to take some questions in and put the numbers in the front so that we can discuss or talk about. I'll love to take any questions if you guys have. Thank you.
As a user of AI, how can I identify whether I'm getting biased answer or not?
That's actually a good question. Few things, how you're getting treated, I would say, and having that lens. sometimes it's a good test to do is something that you know, and then ask the AI that the same question, and you see that the question is not being answered or being answered. Something that's a bit more stereotypical, I would say.
Because most of the time, after using multiple AI tools, I'm getting the same answer.
Mm. That,
The tools may differ, but the answer won't change. So, how can I understand that I'm getting biased answer or not?
that's a really good question. It would take a little bit of deep dive on it. I'm sorry, I don't have an answer for
Oh,
that
thank you.
specifically, but I can follow up with you once I have the answer if you give me your email.
Okay, thank you.
I'm very sorry.
As I understand from your report, a most important factor of um, awareness of trust in artificial intelligence is a technical factor. But what about other factors? Maybe organization one or human factor. How these factors influence of people awareness of AI bias on the level of trust of artificial intelligence? Not only technical, maybe organization or human factor, maybe someone else.
For human factors, um, it's something that, as I mentioned earlier, we all have this idea of AI being perfect and can it do my job perfectly, but we never come with the lens that is AI is treating me differently. And I'm sorry that I couldn't answer her question, but that knowledge is that lens is something that we develop. We see around us, we meet with people, and we discuss and we learn from each other, and have that same lens when we're interacting with AI helps us to know that. And organizations, currently, I would like to explain my own company's architecture that they're doing with AI. Is they're currently trying to take open weights model and training it to its finest tunes. And we have actually brought in EDI personnels to talk and to see if the AI has been tuned perfectly so that it doesn't take out the resumes of a female candidate, of a person who is in color, of a person who is from a different geographic region. And we actually clean the data before giving it to the AI. We scrape out their resumes, any kind of physical factors or writings that might trigger the AI's EDI sense. So we take out those and make sure that, and corporates actually can follow that. They can cleanse the data, give it only what's necessary, and then take AI's decision on that, rather than giving it a fully fledged resume with name, where they're from, background, and stuff like that. I hope that answers your question, by the way.
Thank you. Thank you very much.
Thank you.
Thank you so much for your presentation, sir. I would like to call upon our next presenter. Before I call upon our next presenter, I just request all of you all to please keep in mind that time constraints that we have so that we can finish our session within the limited allotted time period. Requesting our next participant to kindly present their paper, Yasin El Khalidi, presenting a paper on the title From Cryptographic Keys to RF Fingerprints, a Zero Knowledge Framework for Physical Layer IoT Authentication. I request you to kindly take over with your presentation, sir.
Hello, everyone.
Hello, sir.
Do you listening to me? Okay, I will share the screen right now.
Okay. Sir?
Yeah, of course. I'm just giving access to Zoom.
Okay. All right. Can you see? So am I audible to you?
Right now it's good.
Can hear you, yes, sir. Can hear you.
Yeah, of course. So,
Yes, we can see the presentation right now.
okay, thank you. So good afternoon, everyone. It's pleasure to be here. My name is Yasin El Khalidi. I'm from Ibn Tufayl University in Connaughton, Morocco. So I work this project with Mohammed El Khalidi and my colleague Achim and Ashraf. Today I will present our framework named ZK Earth Authentication. The paper is called From Cryptographic Keys to Earth Fingerprint. Here is at WorldS4 2026. So here the main idea. In one sense, we can check if the real device is if a device is real by its own radio signal, not only by a secret key. So this is solve a problem for our solution. Because today, if a stolen secret key can let an attacker pretend to be the device himself. So here is my plan. First, the problem. Second, our framework, the ZK-RF authentication. Third, the security. And fourth, the result on the weak thick dataset. And the last with conclusion and of course, if any question. So for the motivation, IoT devices use the key to prove who they are, but there is a problem. If an attacker steal that key, they can copy it. The network cannot see the difference. Small devices do not have much memory. Full security is often too heavy of them. So many systems use one key forever. So for us, fingerprinting is a new idea. Every radio has a small hardware differences. There is a differences works like fingerprint for this hardware. So we don't need extra hardware for this, like oscillator drift or IQ imbalance. So the gap for existing in approach, the past work solve only part of the problem. Example one, like fingerprinting, is a good at finding device, but it saves the template in the plain text. Example two, like zero knowledge proof. Zero knowledge proof, they protect a key well, but they do not check the real hardware. So non-existing schema unify all properties at once. So let's go back to our contribution. We call it our framework ZK RF authentication. It has 4 points. One, the first one is to combine RF fingerprinting and zero knowledge proof. Two, we have 91.4% accuracy and 2.25% error rate. Three, we have a small proof, only 144 byte for the whole proof, checked only in 3 milliseconds. And four, we also detect unknown devices and we reject around 71% of them. So the system on tree model. Our system has 4 parts: IoT devices, an edge gateway with the Siemens network, a blockchain with a smart contract, a verifier now, a verifier. Now the attacker can listen to the signal, but the attacker can replay all signal also. The attacker can steal the database. The attacker can also try a similar devices, but the attacker cannot copy the real hardware, cannot also not break the cryptography also, and the attacker cannot control most of the blockchain. So let's break down to the protocol overview. Our system has 4 parts. Our protocol has only 3 phases. Sorry, phase one, it's the registration. The device unroll one time. We saved only the hash of on the blockchain, and for the phase two, the extraction, we capture a new signal and we compare it to a saved template. So the phase three is the ZK zero knowledge verification. The device proof the distance is small without showing the real data. Then we save the result on the blockchain, but we never save we save only the hash on the blockchain, not the real data. So the phase one, it's the device registration. Registration happens one time. The device sends 15 frames. The gateway make an embedding and take an average. This gives us a template E sub I. We hash it with Poseidon to get the T sub I. Only the hash goes on the blockchain and the raw template stay on the device, not on the blockchain. So my colleague will present the second phase. I hope my colleague is here.
Hi
Mohammed,
there.
yeah,
You hear me?
yeah, of course I hear.
So I'm Mohammed Khalidi. I will continue the rest of the presentation. Uh, for the phase two or the second phase, Siamese CNN fingerprint extraction, we use a Siamese network. This means two networks with the same weights. Each one has 4 convolutional blocks. After each block, normalization, ReLU, and pooling, at the end, we get one embedding. We train with the contrastive loss. It pulls real pairs closer. It pushes fake pairs apart. We use L1 distance, not cosine distance, because L1 is simpler inside the zero knowledge circuit. It saves about 500 constraints. We also use the raw signal directly. This avoids an expensive FFT step. Passing to the third phase, the ZKP or zero knowledge proof based embedding verification. This is the K part. The prover has 3 secrets value: the new embedding, the saved embedding, and the random number R. One graphic 16 circuits proves 3 things. First, a hash equation gives a public value, C. Second, another hash equals the public template Ti. The third is the distance is smaller than a threshold theta. None of this shows the real data. So at D equals, so the dimension D equals 64, we need fewer than 1000 constraints. This works because we use small integers and because Poseidon is fast. So the result, we have a small proof, 144 bytes, checked in 3 milliseconds. The next slide is about security properties. So we proved 6 security properties. The first one is completeness. The ZKP parts always work. Our classifier accepts real devices around 89% of the time. So the second thing is soundness. The attacker must beat 2 layers, our classifier, and grad 16 together. The success rate is almost zero. So the third part is zero knowledge. Nobody learns anything from the proof. And the fourth one is replay resistance, a new random number plus a non-chain list blocks all replay attacks. The five part is template privacy. The blockchain only stores a hash, not the real embedding. So this hash is a very hard to reserve. Six, the rogue detection. We reject around 71% of unknown devices directly. The next slide is about experimental setup. We test on YZig single
I'm
day
really sorry
dataset.
to interrupt, sir. I request you to kindly conclude as soon as possible as we have crossed that 10-minute mark.
I'm sorry, I didn't hear you.
Requesting you to kindly conclude as soon as possible, sir, as we have crossed our 10-minute mark. It's just a gentle reminder.
Okay. I need 2 minutes to complete. Okay.
Yes, sir. Yes.
Okay, we test on YZig dataset. It's a public dataset. It has 28 Wi-Fi devices. So we keep 5 devices separate as a known device. We used other 23 for training and testing. We used Adam optimizer and the contrastive loss. The next slide is about results, accuracy vs embedding dimension. Table 2 shows the results. The best size is d equals to 64. So here's around 92% accuracy and the 2.25% equals error rate. At d equals 32, accuracy drops to around 84%. At d equals 128, accuracy drops even more to around 79%. Why? 23 devices are not enough for this bigger space. The network starts to learn noise, genuine acceptance, and rogue rejection follow the same pattern. Both are best at d equals 64. The next slide is about comparison and with prior work. So now a comparison with 5 other methods. Our past work and Mira's method gives zero knowledge privacy, but only for a key, not the hardware. 2 RF methods give physical identity, but they save templates in plain text. Go and colleagues give full privacy, but no RF hardware and no rogue detection. Our framework ZK RF authentication is the only method with everything: physical identity, full privacy, and rogue detection. It takes only 517 milliseconds, and it has the smallest proof with 144 bytes. The next slide is about attack simulation and results. So we tested 4 attacks or 4 types of attacks, 100,000 times each. The first attack is replay. It passes the classifier every time, but the blockchain blocks every attempt. Final success 0. The second attack is about interpolation. It's the interpolation. This needs 92% similarity to pass. Attack 3 is random guessing. This fails completely, that's sure. Attack 4, nearest rogue device, our strongest attack. It passed the classifier 29 or around 30% of the time, but Grot 16 blocks almost all of these attempts. The next slide, or the final slide, is discussion limitations. 3 limits to be clear. First is around 71% rogue rejection is not perfect. To be honest, for high security, we suggest combine ZKRF authentication, our framework, with our older ECC proof. Second, speed. Must of the 517 millisecond is proof generation. This is fine for periodic checks, but too slow for real-time control. Also, ESP32 devices do not have enough memory, so we use a trusted edge device instead. Third, our data is from 1 day, 20 devices indoors. We still need to test long-term drift, real channel, and more devices. So to conclude, ZKRF authentication combines 4 things: physical identity, zero knowledge privacy, rogue detection, and the blockchain record. We reach around 92% accuracy and small 144 by proofs. So thank you all for listening. Thank you all for being present here today. I am happy, or we're happy to answer your questions.
So what are the limitations you were saying of your?
I'm sorry, I
So
didn't
What?
hear you.
What are the limitations?
yeah, the limitations we talk about it here. We have a rock detection only 17%. So it's not perfect, to be honest, of course. But for a proof of concept, it's good. It's good result for a proof of concept. We now, just to be honest, for now, we collecting our data to right now. It's about 1 month. We have right now 1.4 terabyte of data. So the next study will be on real data on real devices.
Okay, thank
Any other
One
questions?
more question. One more question, if you please. How does your approach improve the security and privacy on physical layer of IoT authentication
How
on physical layer?
I didn't really got the question. So you ask me how does the air fingerprint and zero proof. I really didn't got the question.
There's a physical layer, maybe in fingerprints, maybe some other types of physical layer identification. How can your approach? How does your approach improve security and privacy
So
on this
to
layer?
explain one of these, because each one alone leaves a gap, the air fingerprint allows identify a device, but store in plain form, it can be stolen. So for us, it's the zero knowledge proof alone protect a secret well, but only proves you when you have a key, not not that you are the right physical devices, but together gives one physical identity.
Mhm.
The other gives the privacy and that for that identity. I hopefully it's the
I will add something about this question. So our framework protects privacy mainly through zero knowledge proofs. The registered RF fingerprint is not stored directly on the blockchain. Instead, we store a cryptographic hash. So during the authentication, the prover uses the new and the registered embedding, not the new embedding. So privately and generates a GROT16 proof showing that the embedding satisfy the required conditions. I hope that we reply or we answer your question good.
Mhm. I understand you. Thank you very
Thank
much.
you so
I
much.
understand this. Mhm.
Thank you so much for your presentation. Now I'd like to call upon our next presenter.
okay. Thank you.
Our next presenter for this session is Arjun Sharma, presenting a paper on the title Hybrid Intrusion Detection System Using Machine Learning, Combining Supervised Classification with Unsupervised Anomaly Detection for Zero-Day Threat Generalization. I request you to kindly take over with your presentation, please.
Yeah, thank you. Evening, everyone.
Good evening, sir.
I hope my screen is visible to everyone.
Yes, sir, it is visible to us.
Yeah, so just excuse me if my voice breaks or my screen gets stuck in the middle as I'm receiving heavy rainfall in my area, so there might be network issues. So just please excuse me. I'll try to sum up my presentation before if there is any issue that arises. So, evening everyone. I'm Aryan, and this is a joint project work with my project guide, Dr. Dipali Bavaskar. We are from MIT World Peace University, Pune, India. Our paper is on gating hybrid intrusion detection system, combining supervised classification with unsupervised anomaly detection to generalize to zero-day threats. I'll walk through the architecture, three evaluation scenarios, and what are the key findings in our work. So let's get started with the problem first. So, why intrusion detection keeps getting harder? Supervised classifiers are excellent at detecting attacks they were trained on, but they fail under distributed shifts. Here's a concrete example: a classifier trained to detect HTTP based denial of service will not catch a DDoS flood, even though both are labeled as DOS. The flow level statistics are completely different, non overlapping distributions under the same level. That's the core tension. Supervised models are precise but blind to the unfamiliar, and most published ideas work only test on a single scenario, which can be hide exactly this kind of failure. So the question we are asking is, can we combine the precision of supervised learning with the reach of anomaly detection without one degrading the other? So here's the contribution towards that. The five things. The first one is our gating hybrid fusion outperforms standalone random forest and gating boosting across three test scenarios with a 40.5% F1 gain on out of distribution attacks. I'll show the numbers in detail after a while. We evaluate on three scenarios, not the usual ones: known attacks, zero-day generalization, and outer distribution robustness. These are the three scenario evaluations. The third one is where our result hits the extreme, like F1 hits the 0% or the recoil is at 1. We don't just report them, we will be explaining backed by a 95% Wilson confidence interval. The fourth is permutation feature importance revealed something actionable. TCP initial window size is the dominant detection signal, which has real evasion implications. And the fifth one is rigorous deduplication, which is present in CIC IDS 2017, that has up to 45.4% of duplicate flows for some attack types. We remove them before any train test split, so our number are not inflated by any leakage. So the whole system rests on one idea. Let me state it simply. So trust the classifier when it is confident, consult the anomaly detector when it is not. A gating network restricts the anomaly detector's influence to uncertain regions of the classifier's output, the zone around its decision boundary. Outside the zone, the supervised model decides alone. Unsupervised noise never overrides the confident supervised code. So is the actual here's how it has actually been wired. So the architecture, it basically goes like a network flow which is having 59 features after the pre-processing goes into a supervised backbone. Random forest outputs a confidence score. Let's say it's P1. The scores go through the confidence gate. If P1 falls outside the uncertain zone, meaning the model is confident either way, its prediction stands alone, unchanged. That's the green path. If P1 fails inside the uncertain, uh, it goes into the uncertain zone. You bring in an anomaly detector, either an isolation forest or an autoencoder, and fuse their scores in P final. Here you can see the formula which we are using. So 1 minus W times P1, PW times the anomaly scores. So the important distinctions of from this architecture is there are two separate hybrid variants, not one combined four model systems. Random forest and isolation forest was grid search to W equals 0.25 threshold, uh, 0.40, and random forest and Norton Goder was grid search to W equals 0.35 with same threshold. Gradient boosting, by the way, is the only used as comparison baseline. It's not part of either gated hybrid. The base components. Two supervised base components, which are random forest, it's having 300 trees, max depth of 20, class weighted balanced, is a hybrid backbone. The gradient boosting is having 150 trees with the depth of 5, is a standalone comparison only. Two unsupervised detectors, both trained benign only so they learn that normal looks like. Isolation forest isolates outliers through random splits. The autoencoder is a small neural network, 59 down to 16 and back up to 59, that reconstructs benign traffic when reconstruction error spikes. That's a novelty signal. So this is the fusion rule. The classifier's confidence score runs from 0 to 1. Below 0.15 or above 0.75, the classifier is confident and its prediction is final. Between 0.15 and 0.75 is the amber zone, where the fusion happens. So we turned variant independently on validation sets. So RF and IF weighs 0.25 on the anomaly score threshold of 40, and way of 0.35 same threshold. The threshold defines exactly how wide the fusion band is around the classifier's decision boundary. The reasoning behind the swall weights is 0.25 and 0.35 is deliberate. Anomaly detectors are noisier than the supervised model. So we let the nudge borderline decision not dominate them. So before the results, a quick word on the data set on why our evaluation is trustworthy. So we use CIC-IDS 2017 dataset, which is the mostly cited dataset when it comes to IDS research. So it is having the 5 days of realistic label traffic, 59 flows feature after the removal of 19 zero variance ones. The critical step here is deduplication. CIC-IDS has high duplicate flow up to 45.4% of the SSH petater, 13.6% even in the pure benign Monday traffic. If you split randomly, duplicates land on both sides of the train as well as the test side, and and the report score is inflated by memorization, not generalization. So we duplicate at the source file level before any split. So there is exactly zero row leakage. From that, we built 5 data sets, training and validation on 8 known attacks, then the 3 held out test sets, known 0 day and stress, which brings me to our evaluation design. So the test known asks, can the hybrid match or beat supervised baseline on what it was trained for? So test 0 day asks, what the test 0 day asks, does the generalize to attack types it's never seen, specifically infiltration and SQL injection. Test stress asks the hardest question: does it survive an out of distribution operating point, 99% benign traffic with DDoS and port scans embedded, versus the 90% benign it was turned on? A single scenario F1 score can hide a total collapse in any one of these. We wanted to know where specifically the system breaks. So let's get through the results in the order, stating with known attacks. On the 13,500 known attack test samples, our best model is gating random forest and autoencoder. F1 of 0.9778, precision of 99.24. That beats standalone random forest at 97.50, F1 and gradient boosting. But the numbers I actually care about more here is the false alarm rate. It drops from 1.80 with plain random forest to 0.76 with the hybrid. That's more than 50% cut in the false alarm, directly addressing the alert fatigue, which is on the biggest operational complaints about the IDS deployments. That's the that's the case of the known attacks. Now the harder one are the attacks that has been never seen. So on 570 samples covering infiltration and SQL injection, neither seen during training, the picture is mixed, and I want to upfront about it. For the SQL injection specifically, gating, random forest, and isolation forest
I'm sorry to
lifts
disturb,
record.
sir. However, we have crossed the 10-minute mark. I'm just, this is just the gentle reminder to kindly conclude as soon as possible.
Sure. Uh, the SQL injection, specifically gating, random forest, and isolation forest, left the recall to 47.6% versus a 33.3 average percent from the supervised baseline, a genuine 14.3% improvement from bringing it to the anomaly signal. But the infiltration recoil is zero for every single model hybrid included. The reason is structural, not a modeling failure. Infiltration traffic uses valid stolen credential at a flow level. That traffic is statistically indistinguishable from legitimate authorized access. This is known as limitation of the flow-based ideas generally. We say so directly in the paper rather than to hide it. So the most interesting result through it, what happened under the distribution shift, are stress tests. Here we take around 15,000 samples, 99% benign and embedded DDoS and port scan attacks, a generally out of distribution operating point. Compared to 90% benign traffic, everything was turned on. Both supervised baselines collapse completely. Random forest to zero and gradient boosting F1 of zero. And here's the part that matters. The ROC AUC stays high the whole time with 94.7% on random forest and 95.8 for GPT. That's the paradox. ROC is the threshold independent. It measures ranking quality, not decision at an actual operating point. So the 90% confidence threshold that worked at 90% benign traffic simply breaks the 99% benign. It stops firing at all. So one more result before I close, something we found almost by accident from asking why the model works. So we ran permutation importance on random forest. One feature stands out overwhelmingly. So the TCP receiver window causes 32.8 percent drop in the F1 when permuted. That's roughly 10 times larger than the next important feature. So with that, I would like to conclude shortly my presentation. So one fusion strategy matters more than the fusion presence. Our gating approach beat simply weighted fusion on all the three scenarios. Simple fusion actually introduced net negative predictions on known attacks. Multiple scenarios evaluation is essential. A single scenario F1 would have completely hidden the out of distribution collapse we found. And third, the importance is actionable, not just descriptive. It told us exactly how the model is vulnerable to evasion. So these are some of the limitations and the future works. So the TCP fingerprinting reliance is evadable. Infiltration detection needs a signal beyond flow level features entirely. And port scans tiny 40 to 80 bytes probes are indigestible from the legitimate service discovery at granularity. We'd also like to validate this approach on the dataset beyond CIC IDS dataset which we have taken. So that's all about the presentation. I'm happy to take on any questions if anyone's having. Thank you.
Ma'am,
Did
sir, do we
you
have any questions? Okay.
did you run the system any in real time or in simulator to get the results?
No, actually, we have not tested it on real time as we have made a dummy servers in our college lab where we tried to carry out certain types of attacks. So that's the only place till which we have like tested our system for now.
Okay. And regarding the data set, that CIC IDS 2017, whether it is a current data set or it is an older one?
It's an old data set, but as it was the most cited data set when it comes to ideas, so we have gone forward with that. On the second half, we were
So if
all,
I am correct, if it is mentioning as 2017 means the data set belong to that year, right?
yeah, 27 is the year which they published the
Uh,
data set.
so now currently we are in 2026. Why didn't you try for the data that is after at least 2022 or 2023?
So, as this was the most cited data set with like broader features which were available compared to their modern data set which they have published, so we have gone forward with this particular data set.
I have a question just to add with Madam.
Yeah,
Currently, we already have CIC IDS 2023, which
yeah,
comes with the newer attacks. So
yes.
I believe it would be better to test on CIC IDS 2023 instead of 2017, which is already old.
Yeah, yes, it was old, but just by keeping that under the consideration that it was more cited compared to the 2023 one, so we move forward with the 17 one. But definitely, we will be giving the 2023 dataset also a try with the model which we have come forward with.
What about like you want to try it with other data sets as well? How many
Yeah, the
purpose you want to try this?
Yeah, the other data set which I was talking about is the data set which we will be making ourselves. Like we will be keeping an ideas on a particular host, and we will be collecting all the network packets, like comparing it
There
year
are
wise.
there are relatively smaller data sets like UNSWNB15, Ton IoT,
Yeah,
right? So if you run it on multiple corpus, maybe it's easier to compare the results. Thank you very
yeah,
much. This is not a question, just a
yeah.
suggestions.
Thank you, sir. Yeah, I will definitely consider the suggestions for the future work. Yes, sir.
Thank you so much for your presentation. Uh, Thank you so much, sir. Now I would like to call upon our next presenter. Our next presenter is Moses Chupanta presenting a paper on the title Influence of Artificial Intelligence, Social Media, and the Legal Basis for the Administration of a Higher Education Institution. Sir, we request you to kindly take over.
Moment, please. Share. Okay, my topic presentation, influencing artificial intelligence, social media,
I'm
and
sorry to interrupt, sir. We cannot see the screen yet.
view. View presentation?
Yes, sir. We can see the presentation.
Yes?
Yes, sir. We can. We can.
Yeah. Okay, continue. My topic presentation, influence of artificial intelligence, social media, and the
I'm
legal
sorry,
basis.
but
I'm
this
so
is
sorry.
not the presentation.
Yes.
This is the agenda of our meeting.
A ver. Y problem share.
So if you could close this slide and just open your presentation, then you'll be able to present it. So you are muted, sir. I cannot hear you.
Share. A ver. Presentation view.
We can see our meeting right now.
Yes, presentation. A ver. Compartir.
So have you opened your presentation already?
Sí, un moment, please, por favor. Moment, please. Ay, ay, ay. I'm problem. View presentation.
Yes, sir.
Okay. My topic presentation, influence of artificial intelligence, social media, and the legal basis from the administration of higher education institution. My name is Moises Tuapanta. I'm from Ecuador and Latin America. Content is introduction, problem, and project, or overall, material and methods, result, future work, conclusion. Introduction. The globalization of information and communication technology, ICT, the internet, artificial intelligence, AI, and social media process serious threats and the internet confidentiality and authenticity of information and higher education institute HEI. Problem and project. The change of artificial intelligence social network and the legal framework for manage higher education institution persists why the globalization, the information and communication technology ICT and adaptive artificial intelligence AI in digital platforms as transferred current regulate the fair privacy and legitimates in the institution information privately do the several regulating framework governance use and security personal day. That our goal, the objective is the determine the percentage of artificial intelligence social network and the legal basis in the administration in the higher education institute material the disfaz where analysis the several documents relate on the research topic using the deductive method analysis insufficient articles, lies, regulation, and official wise. The approach diverse perspectives support file stability, methodology, and validate research method. The research methodology was applied using the mixed methods approach, the deductive method to analyze information or times from ancient articles. Office was while with the side, lies and regulation relate to her education, social media, artificial intelligence, and the legal framework. To conduct this analysis, five sequential aspects measures the considered problem, analysis argument in favor of the artificial intelligence AI argument when in the education free argument relative to social media and argument concern the legal foundation. Result relevant occur in the administration in the higher education institution. Legal base, historical de políticas, recursos humanos, national and international regulation, academic system, ICT infrastructure, hardware, activity, software, education, social network, artificial intelligence, IA, legal base. AI model social media legal basic from the administration or higher education institution, network social communication, diffusion, fairfax, a high school institution, sustainability, innovation, query, artificial intelligence, optimization, prevention, and generative analysis, administration, admin, manager, decision making, legal basic, regulation, compliance, discussion. This research focuses on exploring artificial intelligence, social network, and legal framework for the administration of higher education institutions, identification rates, perspective, regulating key authors, indicators, and the integrated model. No simulation and implementation was conducted in the print. Objective in the initial phase was determined the perspectives and the studio activities from the defined fast methodology which provide structured analysis and general the result present. There's France establishing the foundation understand in the guide where future simulation, prototype, development, and practical application higher education administration. Future work in the short term, in the research shall apply in the higher education institution in Ecuador or in a country wide similar cultural and technology infrastructure when they are in advance and the simulates fast for prototype development and suggest implementation. Conclusion. The study concludes the improving the manager the high education institution require mitigates the risk, vulnerabilities, and trends posed by the use of artificial intelligence and social network through the implementation of appropriate legal framework for IA, relying in the edge country constitution, laws, and regulation. Ecuador alone win most countries in Latin America and in the Caribbean. Either rise, choose legislation or the skills, the process are ready. Finally, is what I included as in the specific case of Ecuador is the from necessary and hungry to establish an adequate artificial intelligence AI law as the day only this bill being submitted to the National Assembly. Again, the author and the praise their gratitude from the Collaboration University Center for Participation. This study will support provided RNAs and AC media. Thank you, email. Thank you.
No questions, sir.
I have one question, if you please. What legal and regulatory challenges arise from the use of artificial intelligence in higher education?
Sí, en Ecuador, la base legal Artificial Intelligence Initial en proyección en Asamblea Nacional, and study, analizan.
Thank you very much.
Thank you. Thank you very much.
Thank you so much for your presentation, sir. With this, we come to the end of our session.
Perdón.
Thank you so much. As I said, with this, we come to the end of our session. I would like to thank all our authors for their excellent presentation and contribution in this session, and all our participants for being a part of this international conference. I hope this session was informative enough. We, on behalf of the whole team, thank you for your support during this 10th version and all the previous 9 versions of this conference. We'll be happy to have you in the 11th version in 2027. All the presenters would be getting their digital certificates through email within 2 working days. The publication will be live within 7 to 8 months. Kindly cooperate with the team of WorldS4 2026. I would like to thank our session chairs for being there for us and being our guide throughout the session. Ma'am, sir, would you like to make any closing remarks before we end this session?
Base legal in constitution in Ecuador, initial, layer superficial, no reglement for institution education high.
Okay, sir. Dr. Alexander, Dr. Uma Maheshwari, ma'am, would you like to say anything
Yes,
before we
ma'am. I
conclude our
would like
session?
to conclude that I feel honored and privileged to be present at this session and to hear the intellectuals from around the world to keep their opinions on artificial intelligence. The sessions were very informative and it actually gave many insights in different domains of AI. So thank you for this.
Thank you so much, ma'am. Sir Alexander?
I would like to thank to all the presenters for your insightful and engaging contributions. Your presentations covered a wide range of important topics, including artificial intelligence, cybersecurity, Internet of Things, authentication, machine learning, and the role of technologies in higher education. We have reports from different countries, from Ecuador, from Bulgaria, from Canada, from many other unique countries. I would like to thank to all participants for their valuable questions and discussions, and it was a great pleasure to chair the sessions, and I wish you all continued success in your future work. Thank you.
Thank you so much, Professor.
Please unmute your microphone. Unmute your microphone, please.
Yes. This is a token of appreciation to the chair on behalf of Team World S4 2026 and Global Knowledge Research Foundation and partners. Thank you so much all for being a part. Now, I just quickly request all of you all to please switch on to your cameras so that we can have a quick snapshot of this virtual session we just attended. Requesting all our participants and our guests to kindly switch on to your cameras, please.
Just a minute.
All present, I request please kindly switch on to your cameras. Thank you so much. We'll meet you in the next session, 2027. Thank you.
Thank you so much.
Thank you so much. Thank you so much for being a part.
Thank you for sharing.
Thank you.
Thank you.
Thank you, everyone.
Thank you. Bye.
Bye, ma'am.